Welcome scholars to Advanced Higher Physics Unit 1 Section 2. Section 2 is called Angular Motion. This particular part, 1.2.1, is on angular displacement, angular velocity and angular acceleration. I've spread this over 2 lessons. This is the first of the 2. Here then are the learning outcomes for the first of these 2 lessons. There are 3 of them, and you can see that the first one introduces us to the idea of angular velocity omega, and to define omega we need a concept of angular displacement theta, and omega will become d theta by dt, as we'll see soon. Secondly, we'll look at angular acceleration given the Greek letter alpha, and we'll use both of these, or all 3 of these in fact, these terms in what essentially are angular equations of motion. Okay, so it's going to be fun. Let's get going. Right, so let's define what we mean by a radian. We're going to define an angle in radians. So we begin with a circle, center O, as you can see. It has radius r. And what we're going to do, as you can see, is draw 2 radii which encompass an angle theta, as shown. And that produces an arc of length s, that curved arc, as you can see. So circle, center O, radius r, and it subtends an angle theta, and that produces an arc length s. Okay, those are the ingredients required. Let's put them together and cook up our definition. Well, we define the angle theta in radians very simply as theta equals s over r. That is the definition of an angle in radians, the arc length divided by the radius. Now remember that once we've got a specified circle, the radius r is constant. So the bigger the arc length is, the bigger s, obviously the bigger the subtended angle will become. Okay, let's imagine then that we let theta be 360 degrees, one complete revolution, if you like, right round the circle. Well, when theta is 360 degrees, we know that our arc length must be the entire perimeter of the circle. Now you know from your lower school maths that the perimeter of a circle is given by 2 pi r. So when we apply our theta equals s over our equation, we get 2 pi r divided by r, the r's cancel, and we get 2 pi. That tells us then that 2 pi radians is the same as 360 degrees. 2 pi radians is 360 degrees, or another way of thinking about it is the angle of a circle is 2 pi radians. It follows, of course, that pi radians is therefore 180 degrees. So that's something you should commit to memory. Okay, so we have defined the angle in radians. Let's now move on and define angular velocity. So to do this, I want you to imagine a particle moving in a circle. You could imagine yourself on a merry-go-round going round in a circle. It's a similar sort of thing. This particle starts off at position P as shown. The circle has center O, and after a little while the particle has moved from P around the perimeter to P dash, and that sweeps out an angle theta. So particle P moving in a circle, center O, sweeping out an angular displacement theta, and let's imagine that happens in a time t. Well, we're now going to define the angular velocity of the particle P. It's given the name omega, the Greek letter omega, and the definition of omega, angular velocity, is quite simply the angle swept out, theta, divided by the time taken, t. Compare that with the definition of linear velocity, which is the displacement s divided by the time taken, t. It's very similar. So omega, angular velocity, is theta over t, the angle swept out divided by the time taken to sweep out the angle. That would be regarded as an average angular velocity. Theta is finite, so is t. We can define the instantaneous angular velocity of the particle, and remember from the previous section, an instantaneous expression is one where t is vanishingly small, approaching 0. So to do this, we use our d notation, and I'm sure you can predict that omega as an instantaneous angular velocity will be d theta by dt. Units, well, omega is a number of radians divided by a number of seconds, so it's measured in radians per second. And just to recap, omega, which equals d theta by dt, is the angular equivalent of v, which equals ds by dt. And finally, in this lesson, we move on to angular acceleration. Well, you'll recall that in linear motion, the acceleration of a body is given by dv by dt, so we simply convert that into angular notation, and we get d omega by dt. Now, so that we don't get mixed up between angular acceleration and linear acceleration, we call angular acceleration alpha. And this alpha is, of course, measured not in meters seconds to the -2, but in radians seconds to the -2. So alpha equals d omega by dt, and that can also be written as d2 theta by dt squared, just as linear acceleration is dv by dt or d2s by dt squared. Alpha is the angular equivalent. So we can line up now in a table the three linear equations of motion and their angular equivalents. So here are the three main linear equations of motion, and their angular equivalents in each case are, well, for v equals u plus at, we have omega equals omega naught plus alpha t. We call the initial angular velocity omega naught and the final angular velocity omega. S equals ut plus half at squared in rotational terms becomes theta equals omega naught t plus a half alpha t squared. And finally, v squared is u squared plus 2as becomes omega squared equals omega naught squared plus 2 alpha theta. And that's the end of the first lesson.